Hi everyone, welcome to this Learning R course. This is session 4, creating a model with R using for loops and if-else statements. This is the overview of this R course, and we are at this stage now. All of the R code and other files are on GitHub. Go to github.com/edmundryan. You'll need a GitHub account in order to download the files for session 4 and other sessions. So in the previous session, we trained and carried out diagnostic checks for a linear regression model, but I didn't show you how to use the model, how to apply it for a new input point. And I'm going to show you this now because this is important for the rest of this session. So in the second example from session 3, we were predicting the miles per gallon of a car from its cylinder, displacement, horsepower, and weight. And the model is given down here. And the betas represent the parameters, sometimes called the coefficients. And then you've got the three inputs here, the displacement, the horsepower, and the weight. So this is the R code that you would use. I'm not going to actually do this in practice. I just wanted to show you, but feel free to pause the video and copy it out into your RStudio session. And also this code is self-contained, so you don't need to go back to session 3 in order to apply this example. So you've got the linear model, which we've trained, and mtcars is an inbuilt data set within R. And we then do a summary of that linear model. We call it S1. And we're going to create a single point, which at this point we generate the three variables of that input point separately, so the displacement, horsepower, and the weight. Now I've ignored the correlations between these three input variables. There might be some combinations that aren't physically possible, but this is just to demonstrate how it would work. And then you can output these the three input variables for the single point. And then we need to extract the parameters for the linear model. So if you do names S1, this gives you lots of the different things that are stored under the linear model. And then the coefficients is what you need for the parameters. And then we're going to call that param, and we're going to store it as a vector. And then to actually get a prediction from this single point, you would do this line at the bottom. So the param refer to the four values. So the first one is the y-intercept, and then you've got the other three are corresponding to the three input variables here. And then you get your prediction. So in this session, we will train and apply 3 multinomial logistic regression models. And these models, I'm going to refer to them as submodels, will join up to allow us to build a large model that simulates a cricket match. In particular, it's going to simulate the first batting innings of a 2020 cricket match. The model will also consist of various for loops and if-else statements, and we'll bring together other aspects of this course like subsetting. So I'll talk about for loops and if-else statements in a few slides time. So what is multinomial logistic regression? Well, it's similar to linear regression, except that what you're trying to predict only takes a fixed number of values. So for example, if there are only 2 possible outcomes, such as y equals 1 and y equals 2, then you would get this is your logistic regression equation. Now you can think of the 2 possible outcomes as being, say, for example, if you wanted to predict the outcome of a biased coin, then this might be appropriate. So the right-hand side is very similar to traditional linear regression. You've got your parameters, your coefficients, the betas, and then you've got your x's, which are the input variables. And then, but the left-hand side is different. So the PR here refers to the probability of the first outcome, y equals 1, and the denominator here refers to the probability of the second outcome, y equals 2. And log here is the natural log. And this, when you do this, what you'll find is the resulting number will be on the real line. So it'll be a number between -infinity and +infinity. Then to extract the probability of of the first outcome, we would apply this formula, and then because the probability add to 1, we can work out the probability of the second outcome as being 1 minus probability of the first outcome. Now that's just 2 possible outcomes, but let's say we had m possible outcomes, then you'd actually, rather than 1 equation, you'd end up with m minus 1 equation, so it gets more complicated. And I'm not showing this in order for you to be able to understand it and fully get. I'm just showing the maths here for those that are interested, but it's not necessary to understand this R course. It's just to outline what the maths is. So you get m minus 1 equations that are very similar, but you end up with the parameters, and the left hand side is different in each case. And to work out the probability of y is equal to m, small m, which takes values 1 to up to capital M minus 1, you use this formula here, and then probability add to 1. This is a similar formula to before. Here we're just going to consider a 3 outcome multinomial logistic regression, and we're going to do this 3 times for each of the 120 balls in the cricket match. So just to say that this, although we're simulating a cricket match, it's not in it's okay if you don't know the rules of cricket match. In a nutshell, you've got 120 balls that are bowled, one after another, and the batsman has to try and score runs in each of those balls. There are 11 possible batsmen, so if the batsman gets out, then a new batsman comes in, and they can score. There are 7 possible outcomes: 0 runs, 1 run, 2 runs, 3 runs, 4 runs, 6 runs, or a wicket. It is possible to get other numbers of runs, like 5 runs, but these are very rare. And in fact, in the training data we're going to use for this model, there's no instance of 5 runs or 7 runs or anything like that. Now, I could have used a multinomial logistic regression with 7 possible outcomes, and that would have been fine, but it's quite complicated because it would involve 6 different equations, may have been computationally quite expensive. Probably a better way of doing it is to have 3 separate logistic regression equations that each have 3 possible outcomes. And the reason why this might be computationally better is because in the first model, you're only predicting 0 runs, 1 6 runs, or wicket. Now, if you get 0 runs or wicket as the outcome of that particular ball, then that's it. You go to the next ball, and your cost has been, your computation cost has been quite low. You only go to the second submodel if you need to, if you've selected the second outcome, 1 6 runs. And here we predict 1 3 runs, 4 runs, or 6 runs. Now, I should just clarify that 4 runs and 6 runs are what's called, you get if you get a boundary around the outside of the cricket field. There's a boundary rope, and if you hit a ball and it reaches the boundary, then you get 4 runs automatically, even if you don't actually run 4 runs. Your 4 just gets added to your total as a batsman. You get 6 runs if you clear the boundary rope and it doesn't touch the ground before it reaches it. And then you get 1 to 3 runs if you scored the runs and you've been actually running between the 2 wickets with the other batsman. And then the third submodel is used if the 1 3 runs outcome was selected from the second model, and then it has these 3 outcomes. So for each submodel, we compare a random number between 0 and 1 with the probabilities of each of the outcomes to determine which outcome to select. So this seems quite general and quite kind of theoretical. It'll become clearer when we actually show you the actual R code itself. So the model will involve 2 for loops and various if-else statements. So a for loop is used a lot in models. Because we are running the model for 120 balls, each of those balls, they're kind of the mechanics of calculating which of the 7 outcomes to select is the same set of R code. We're just repeating it again and again, but obviously when I say repeating it, we're repeating the lines of code, but we're getting a different outcome each time because of the probabilities that are selected within that, and also because of the input files might have a different batsman in place, for example, for different balls. So the for loops are a way of looping between maybe lots of different, say, time steps or different steps within the model. And if else statements are selected where there are, you need to select a particular option based on a condition, and it will become clearer when I show you the R code for it as well. The predictor variables for each of the submodels there are just 3 of them: the batting average of the batsman. So this is the number of runs they've scored on average in previous matches. The power play status. So power play is a period in the game where the fielding team have to be in a certain kind of setup, have been a certain kind of fielding setup. This fielding setup allows the batsman to score more runs, but it's only for a certain period of the game, and both teams are allowed to have it. So it's just a way of encouraging more runs to be scored in the match. The type of bowler, whether it's a spinner or a pace bowler. So a spinner, as the name suggests, spins the ball. It bowls the ball slower, but because of the spin, can sometimes cause the batsman to misplay the ball or to miss the ball, and therefore the spinner can often get wickets. The pace bowler, as the name suggests, is a bowler that bowls very fast balls and can uses the pace to try to get the batsman out. The training data consists of 14 home matches, data from 14 home matches for the Durham County cricket team. We're using data of first innings only, where Durham were batting, and this is a 20-20 match, so this involves 20 overs, and there are 6 balls per over, so 120 balls in total. Validation data, so there's a 15th match we used for validation. This wasn't used for training. We ran the model then I'm going to show you we're running the model for this 15th home match, and it's a way of checking if a model is performing well or not. So the inputs and outputs look like this. The actual real inputs that we need is power play, spin bowler, and batting average. These other inputs are just there to indicate what these rows refer to. So you've got match number 1 to 15, innings, the over, and the ball number within each over. And then the outputs consist of the different 7 possible outcomes you could get for each ball that's bowled. So each row here refers to different balls that are bowled one after another. And this isn't the complete number of rows. It goes on further. If it's 120 rows, 120 balls per match, and there are 50 matches in total, 14 used for training and 1 for validation. So I'm going to show you the R code now. But before I do that, I'm just going to show you the actual training data. So this is what it looks like. This is what we will read in, and you can see it goes all the way down to 15 matches, and you've got just under 1,700 rows. So 1,700, just under 1,700, lots of data to be able to use. Now, if I was doing this in a very rigorous way, I might use more data to train it. But this is it's always good to use smaller amounts of data to begin with, and then you can always build up to more complicated models and data later on. So let's go to the actual R code itself. So we've got 2 R scripts here. The first one's going to be estimating the parameters of each of the 3 logistic regression models, and then the second R script will be actually running the model using those parameters and other inputs. So when you start any R script, it's good to have first a description about what that R code is doing. So I've described it here. This is useful for particularly for other people that are reading your R code, but also for yourself if maybe you write some code and then you don't look at it for 6 months, and then you look at the code again. It can be helpful to remind you about what you were doing when you wrote it. Next, we want to remove all current objects in the R environment. I've got no objects here, but if you have been using R previously, then that can be a good way of it's important to remove them, just because if you've used the same variable name as previously, or you've made a mistake. I found this sometimes, that I've thought I've created a particular variable, but I haven't, but another variable with the same name was created in the previous session, and that can cause confusion. So it's important to clear everything, and then if you do find any errors, it will become clear. We next install and load any R packages that are needed. So I've commented out this install.packages function, but this you'd run this line for the very first time that you run the R code to install the particular package that you need. But once you've run it once, you never need to run it again, unless maybe you want to update. There's maybe a newer version of the package. Maybe you might want to install it again. And then we run library to load that package. Every time we run this R code, you run library of that package. We set the working directory. This is where the files are stored, and we're going to read in the data. So this is the CSV file that's just referring to. And next we're going to build the submodel once. This is the first logistic regression model that has the following outcomes: 0 runs, 1/6 runs, or a wicket. Now this first bit here, this is subsetting, where we're removing rows from the data set where there were NAs in the batting average. Some of the rows had NAs in the batting average column, so we need to remove those first before proceeding. And then we would use that index to select the correct rows we need for the inputs and the outputs. And the inputs are for the first 9 columns, and the outputs are the columns 10 to 16 of the cdata.in. This is the CSV file. And of the outputs, we are going to assign 1, 2, and 3 to different outcomes. So the first column refers to 0 runs, and the second outcome, we're going to combine these columns 2 to 6 because they refer to scoring runs 1, 2, 3, 4, 6. And then the third outcome is a wicket, and that's the 7th column of the actual data file itself. Now, there's quite a lot of columns that are in the training data CSV file, but we don't need them all. We just need 4 pieces of information, so we're going to create a new data frame and just combine them all into one place. So we have the power play variable, the spin bowler variable, the batting average input variable, and then the outcome. This is the output of the model. And so 4 of these, apart from the batting average, 3 of these are categorical variables. The power play can only take 0 or 1, spin bowler can only take 0 or 1, and the outcome can only take 0 or 1. I'm actually just going to run all of this now. It's just going to show you how that is. So you've got power play, and I'm actually going to do a head of cdata m1. So you can see here you've got ones. They can be, power play can be 1s or 0s. Spin bowler can be 0s or 1, and then batting average, and then outcome can be 1, 2, or 3. So for the categorical variables, we need to tell R that these are categorical variables, because if you don't, then R will think that the 0 and the 1s and the 1s and 2s and 3s will have some numerical meaning, like that 3 is bigger than 2, that has some kind of numerical meaning, but it doesn't. I could have used A, B, and C if I wanted to. So this factor function just tells R that these are categorical variables. And then we build the actual model. We train it. This is a way of using everything, all of the data, to estimate the model parameters. And then the summary, this is stores all of the different outputs of that. So I just do that. And if I do names of S1, they can see all different types of output variables that are created. Now the coefficients is the thing that we're going to need. These are the parameters that are created. So I can actually just show you that if I do S1 $ coefficients, and then you can see that these are the coefficients that we need for the first submodel. Okay, and then the second submodel is pretty much exactly the same in terms of the code. There are some differences though. We filter out the rows where for the outcomes that we don't need. So where there are 0 runs, a 0, there are 0 runs, or where the outcome was wicket. Because in the second submodel, we're only predicting outcomes that consist of 1 to 3 runs, 4 runs, or 6 runs. And then we list, as before, 1, 2, and 3 referring to these outcomes, 1, 2, or 3. And then it's the same as before. Everything's the same. We call our model Model 2, and we call the summary of Model 2 S2. So Model 3 is the same, except for the different outcomes, 1 run, 2 runs, or 3 runs. Call it Model 3, and call the summary of that S3. And then finally, we store S1, S2, and S3, the summaries of the 3 different models, the 3 different logistic regression models as this R data file. So I'm just going to run all of this now. And what you'll notice is that in your folder, you've created a new R data file has been created. All right, we've done that now. That's great. Now this is the second R script. This actually is running the actual model itself. So it's before we're just going to, this again is the description of what the R code does. And then we're going to clear our workspace. And we're going to specify a few things. So I've put this even before setting the current workspace. When I'm running a model, using R to run a model, one of the first things I like to have at the top of the code is the things that I might change between, maybe if I was to simulate a different match. I'm simulating match 4 of the 15 matches. This is the validation match. These things might change. Or if I'm simulating, say, a 50 over match rather than 20 over match, this would change. So it kind of gives it the kind of flexibility to be able to do that rather than hardwiring things in. Now I know for this particular match there were 20 overs and 11 of them were bowled by spinners. Normally I might not know how many overs are bowled by spinners, but I could, if I was wanting to predict the outcome of a match that's going to happen in the future. This match has already happened, so I know that. But if I was going to predict a match that hasn't happened, I might look at how many bowlers are in the team. So let's say there were 4 bowlers, let's say 2 of them were spinners, then I could approximate that 10 out of the 20 overs would be bowled by spinners. That may not be exactly correct, because the actual number, the actual who bowls what over often can change, or it's quite dynamic about which bowlers come into play depending upon the batsman that they're in and all the conditions. So these things are uncertain, but you can estimate what they might be. So the current working directory as before. We don't need to do this again, but I mean, if you already estimated parameters in the previous session, say a few weeks ago, yeah, you would need to run this again. We're going to load the model parameters. This is our data file we created. We're going to load the batting averages. Now, this is a new CSV file. So this gives the batting averages for this match that we're going to simulate. And what this is this is just one match. It only has this number of rows. And the batting averages, these are the different batsmen that were used in this in this match. And so these numbers correspond to different batsmen, and I just simply copied these down and I put them into a new CSV file just to make it easier to kind of to read that in. Great, and now we need to create two of the input variables to run the model. So one is power play. This just consists of zeros and ones. Now the first 6 overs of the 20 overs are power play. So therefore I can create a list. The first 6 numbers of that list are ones and the remaining 14 are zeros. I now need to create the other variable is the which overs the spin bowler will come into play. So I first need to calculate the probability of spin. That's the number of overs of spin, 11 divided by number of overs, 20, 11 divided by 20. And then I can generate a random number from the Bernoulli distribution, which is the same as a binomial, but with n is equal to 1, using that probability. And I can generate 20 random numbers. So if I was just to run all of that, I can show you what it looks like, and then if I actually output that. So you can see here that we've got zeros and ones. The ones indicate the overs where there are a spin bowler came into play. And before we run the model, we need to, I've created a function. And the reason why I've done this is because these lines of code are going to be evaluated 3 different times in the model. And rather than writing out these lines of code 3 times, a more efficient way of doing that is to put them in a function and then just to evaluate that function every time we need it in the model. This particular function is taking the parameters of the model, the coefficients, and the 3 input variables, and then it's calculating the probabilities using the inverse logit formulation of that corresponds to the particular submodel. Now the coefficients, these will vary according to the different submodels that are used, but I'm using the same input variables for each of the submodels, so these won't change. We then need to create some empty lists for storing the things we're going to output. So these are the number of runs in each of the balls, 120 balls that are bowled, and number of wickets. Number of wickets will be either 0 or 1. So this will tell you the location of where which particular balls the wickets were taken. And then finally, before we actually run the model, we need to initialize a few things. These are numbers that will that are dynamic, i.e. that will change as you run the model. And then, so the wicket.count is all described here. This keeps track of number of wickets, i.e. number of batsmen that are out. And this is important because when we get to 10 wickets, then basically the innings is over. No more runs can be scored. Now in a normal match, I would the innings would just stop. But actually, my model, I make all of the matches have 120 balls. But if you get to 10 wickets, then there are just 0 runs scored for the remaining balls. Batsman.car stands for the current batsman, and this is 1. So this is the batsman that's currently in play. And the batsman.count, this is initialized as 2 because 2 batsmen come out to the crease to play, I should say, to begin with, and there's always 2 batsmen that are in play. This will, as you get a wicket, this will increase by 1. So this is the number of batsmen that are batting or have batted. And this is useful because it will, when we're trying to, for the batting average, this helps us kind of as a proxy for the kind of ID for the particular batsman that's in play. And the BA is short for batting average of the 2 batsmen that are in play. So these will vary depending upon which batsmen are in play. If a wicket falls and a new batsman comes in, this will be replaced with a particular batsman. So batsman and the batsman, BA batsman current, is the batting average of the batsman who's currently at the crease, who's currently going to be at the receiving end of the bowling ball. All right, now we're ready to run the model. So we've got 2 for loops here. I could have written this as just one for loop going from 1 to 120, but it's a bit simpler to do it as 2 because the variables we're using, power play and spin bowler, they vary by over. So therefore having 2 just makes it a bit easier. If I had it as one for loop, I'd have to create a list of it would be more complicated to create a list of 120 zeros and ones for these 2 variables. And so then ball.num is the actual ball number that goes from 1 to 120. And then I've just explained this before about the wicket net count being less than 10. So if it's 10 or more, then it means that all the batsmen are out. Well, there's only 1 batsman left, basically. You have to have at least 2 batsmen in play. And so only when we have this condition is satisfied, then we can actually run the model. But if it isn't the case, then we just say that the number of runs scored in that ball is 0 until all 120 balls supposedly have been played. So next we calculate the probabilities of the 3 possible outcomes from submodel 1, which is 0 runs, 16 runs, or a wicket. And we're using this function calc.prob. So this is this function I listed up here. So this calculates the probabilities from the first submodel, and then we've got our 3 different variables here. And we generate a random number between 0 and 1. And then we use if-else statements to determine what we should do. So if the random number is less than the first probability, then our outcome is 0 runs. If it's less than the sum of the first 2 probabilities, then we select the second outcome, which is 1 to 6 runs, and otherwise it's going to be a wicket. Now if it's a wicket, this has consequences. This has a number of things that will result in this. First, number of runs that scored is 0. Number of wickets. This is a list of zeros and ones. So this is changed to 1. This indicates that a wicket has taken place. I'll get onto need.model later. Wicket.count this counts the number of wickets. This increases by 1, as does the batsman count. And then this remaining if statement, this basically says whichever batsman has got out, replace the batting average with the current batsman that was in play with the one that is about to go into play. So the batsman.count, if the next will go up to 3, so this lists the third. This refers to the third batsman basically. And then, need.model2, this is listed as 0 or for when you got 0 runs or wicket, but it's listed as, it's given as 1. This variable is given as 1 when you have 1 to 6 runs. So this variable basically says whether or not we should use the second submodel or whether we just need to move to the next ball. So if we do need to use the next model, then it's the same things as before. Almost the code is quite similar to what we've seen up before. We use this function calc.probs, but now with S2 rather than S1. And this we use if-else statements, but we have different outcomes: 1, 3 runs, 4 runs, or 6 runs. And need.model3 is 1 if it's the first outcome, but 0 if it's the other 2 ones. Okay. Right, And then if we use the third model, then it's the same setup as before, 3 different outcomes, 1 run, 2 runs, or 3 runs. And then finally, the third submodel is the first time where we can have an odd number of runs. If you have an odd number of runs, because there are 2 batsmen in play and they're running back and forth between the 2 wickets, the two sets of stumps, I should say, that if you get 1 or 3 runs, then the other batsman is going to come into play. It's going to be the one that's going to be at the striker's end after you've completed those runs. And so if that happens, then the batsman who's the kind of current batsman needs to change around. So this CFL statement takes that into account. Right, and then this is everything. And then these 4 lines here refer to some output, things you might want to output. So num.runs is a list of numbers that list the runs that were scored for every ball. We can then sum them up to give the total score for that innings. Num.wickets is a list of numbers that are either 0 or 1 that indicate what ball the wickets were taken. And then wicket.count is the number of wickets that were taken in that match. And in this particular match, there were 131 runs that were actually scored. So we'll see how close we get to this. So I'm going to select all and then run it. And you can see that we got 179 runs in this simulated match, 5 wickets. So we are over predicting the number of runs that were scored, but I'm not really too bothered. I didn't build this model to at least to begin with, in order to get a really accurate model. It's rare that when you start out with when you start building a model for the first time, particularly with one that's simple, that you get a really accurate model first time round. I'm happy with the fact that it's in the right ballpark. Most 2020 matches score between 150 and 200 runs. Some do score more than that and some do score less than that. But the fact that it's in that range and it's not like, say, 400 runs or 50 runs, I'm really pleased with it. It shows that even with a very simple model, with only 3 different input variables used to make the prediction, I can actually simulate a pretty decent looking score, pretty realistic score, that in a different match that might be quite similar to what it actually is. Now, if I'd included more variables, for example, if I'd included, say, had the accuracy of the bowler, that's called the strike rate, which gives an indication of how likely they are or how good they are at taking wickets and conceding runs, then that is a way of differentiating different types of bowlers, and certainly that could have helped to get a better prediction of in this model. And there'll be maybe other variables I could have included, for example, the weather at the time of the match. If the ground was quite maybe damp, or if it's been quite dry, that has an impact on how fast the ball travels when it's being bowled, or how fast it goes along the outfield. Other things to do with, I don't know, I can't think of other variables that you could include, a whole list of other variables that could have a big impact in the accuracy of your model. But like I said before, when you start out with a modeling, it's better to start with a simple model, and then you can always add details and complexity later. If you start out with a very complex model to begin with, you're more likely to make mistakes, you're more likely to make errors in the model, less likely to understand how it works. Better to have a simple model that you understand. And this also goes with the amount of training data. Some people they like to have millions or thousands of rows of training data, and it ends up being very complicated, takes a long time to run. Start with a simple model and then work up in complexity if you feel you need to. The other advantage about starting with a simple model is that sometimes you find that the simple model does a really good job at simulating the real behavior that you're trying to mimic. And if that's the case, then that's great, because a simple model is always preferred to a more complicated model if it can do the same job. There's no point using a more complicated model if you're not getting any benefit from the extra complexity. So that's all I wanted to say about the modeling. Just one last thing is about task 2. So this is for you to do on your own. I want you to take the second R script I've shown you, the one where we ran the model, and I want you to create another for loop in order to be able to run the model, quick model, for 5,000 repeats. Now I could run the model, actually, I didn't show this, but I could, this is an example of a stochastic model. So I run it again, I actually get 218 runs. I get a big score. If I run it again, I get a different score, 157. So there's a lot of variability in the number of runs that I score in the model. Now I could do this, I've done this 3 times, I could do it 5,000 times manually, but that's will be very slow going. So you can, it's a far quicker way of simulating 5,000 repeats would be to implement another for loop. I want you to see if you can do that. There will be other things you need to think about as well, about things that are initialized. Maybe you might need to create another data frame to store things. So just some things for you to think about. And I'd like you to then calculate the mean total number of batsman runs in the match for each model repeat, averaging over the number of repeats. So you get 5,000 numbers, and then from those 5,000 repeats, and then work out the mean of those 5,000 numbers. And then the third point would be to create a histogram of those 5,000 numbers and look at the distribution of the total number of batsman runs in a match. This is for you to do on your own, and as I said, and I won't be obviously be checking or if you've done it correctly, but I will go through this next session. But it's an opportunity for you to try to practice. If you are serious about getting good at coding, then these tasks are a great way for you to be thinking for yourself and trying to figure stuff out yourself and learning yourself. So I hope you do have time to do this, and I look forward to seeing you at the next session. All right, thanks so much. Bye.